Have you ever been staring at an equation and the x you need to find is just stuck up there in the exponent? Yeah, it's a classic problem. But don't worry, in the next few minutes, we are going to completely demystify powers and logarithms. We're going to give you all the tools you need to absolutely ace your next exam. So let's dive right in.
Okay, so think about this for a second. We all know that 10 to the power of 2 is 100, right? And 10 to the power of 3 is 1,000. So for 10 to the power of x to equal 750, well, that x has got to be somewhere between 2 and 3. But how in the world do you find the exact number? Well, this right here is the very reason logarithms were invented.
So here's our game plan for today. First, we'll do a super quick refresher on powers, get our foundation solid. Then, we'll unlock the big secret of logs and see how they're the inverse of powers. After that, we are going to master the log rules. This is your exam toolkit right here. We'll touch on the difference between common and natural logs, and finally, we'll put it all into practice with some real-world examples.
Okay, first things first. Let's start on some familiar ground. Before we can really tackle logarithms, we have to make sure we're all on the same page with the fundamentals of powers, or as you probably know them, exponents. These are the building blocks for everything that follows.
So what even is a power? It's really just a neat, tidy shorthand for multiplying a number by itself over and over again. When you see something like x to the power of a, that x on the bottom is our base, and the little a up top, that's the power, or the exponent. It's just telling you, hey, multiply the base by itself this many times. Simple as that.
Now these 5 rules right here, this is your power toolkit. Seriously, burn these into your brain. When you multiply two terms with the same base, you just add the exponents. Easy. When you divide, you subtract them. And if you raise a power to another power, you multiply the exponents. Oh, and don't forget, anything to the power of 0 is always 1. And a negative exponent just means you flip it and put it under a 1. Getting these down will make logs feel like a walk in the park.
All right, now that we're warmed up with our power rules, it's time to introduce the main event, the logarithm. This is the magic tool that finally lets us get that x down from the exponent and solve the problem. If there's only one thing you remember from this whole explainer, let it be this. Logarithms are the opposite of powers. They undo each other. They're inverse operations, exactly like how addition is the inverse of subtraction or multiplication is the inverse of division.
And this relationship right here is everything. The exponential form a to the power of b equals r can be totally rearranged into its logarithmic form. A log is just asking the same question, but in a different way. It's asking, hey, what power, b, do I need to raise this base a to in order to get my result, r?
Let's see it in action. Say we need to solve log base 3 of 9. The first step is to flip it back into its power form. So 3 to what power, x, gives us 9? Well, we know we can rewrite 9 as 3 squared. And just like that, we have 3 to the x equals 3 to the 2. And if the bases are the same on both sides of the equation, the exponents have to be equal. So x equals 2. See? Not so bad. Okay, now we get to the really good stuff. Your secret weapon for the exam. Just like powers have rules, logarithms have their own set of rules that let us take complicated problems and break them down into super simple steps. Let's master these. First up is the addition rule. When you're adding two logs that have the same base, it's exactly the same as taking the log of their product. Now think about that for a second. Logarithms turn a tough multiplication problem into simple addition. That is an incredibly powerful shortcut.
So for example, what's log 5 plus log 2? Now you'll notice there's no little base number written. Whenever you see that, you can assume it's the common base 10. So, using our rule, we combine them into the log of 5 times 2, which is just log of 10. And now the question is simple. What power do you have to raise 10 to get 10? Well, that's just 1.
And it follows the exact same logic for subtraction. The subtraction rule tells us that subtracting two logs is the same as taking the log of their division. So, once again, logs are simplifying our lives, turning tricky division into basic subtraction. Are you seeing the pattern here? They make things easier.
Let's try a quick one. Log 6 minus log 2. We just apply the rule, and it becomes the log of 6 divided by 2. And that simplifies beautifully down to just log of 3.
Now this one is an absolute game changer. The power rule lets us take an exponent from inside a logarithm and just bring it right out front as a multiplier. This is the key. This is how we get that x out of the exponent and onto the main floor where we can actually solve for it. Let's look at log base 10 of 10 cubed. We can use that awesome power rule to grab that exponent of 3 and bring it out front. That leaves us with 3 times log base 10 of 10. And remember, the log of a number to its own base is always 1. So it's just 3 times 1, which of course is 3.
Okay, so you're not always going to see the little base number written out. And depending on what subject you're in, chemistry, physics, finance, you're going to run into two very famous types of logarithms, and you need to know what they are.
On the left, we have the common log. If you see log just by itself, it's your cue to assume it's base 10. It pops up in things like the pH scale or decibels for sound. Then on the right, we have the natural log, written as ln. Now this one uses a very special irrational number called e as its base, which is roughly 2.71. Just think of e as the universe's natural constant for growth and decay, which is why you see it everywhere in calculus and biology. And here is a super handy exam tip. Sometimes you'll need to switch between these two. To change a natural log into a common log, all you have to do is multiply by about 2.303. Definitely keep this little formula in your back pocket.
Okay, we've gone over the definitions, we've mastered the rules. Now let's put it all together and see how these tools are actually used to solve a real problem, the kind you're definitely going to see on something like a chemistry exam.
One of the most classic real-world applications of logs is the pH scale, which, as you probably know, measures how acidic or basic a solution is. And the formula for it is right there. pH is equal to the negative log of the hydrogen ion concentration.
So let's do it. Let's find the pH if the concentration is 2 times 10 to the negative 3. We start by plugging that right into the formula. Okay, now we have a log of a product, so we use our addition rule to split it into log 2 plus log 10 to the negative 3. Next, we see an exponent, so we use our power rule to bring that negative 3 down in front. Now we just need to know that log 2 is about 0.3 and log 10 is 1. The math inside the parentheses becomes 0.3 minus 3, so we get a final pH of 2.7.
And here it is, your final cheat sheet for review. Screenshot this, write it down, whatever you need to do. You've got the 3 big rules. Addition becomes multiplication, subtraction becomes division, and you can bring that power right down in front. And don't forget the 2 basic truths. The log of the base itself is always 1, and the log of 1 is always 0.
So, we've seen today that the real magic of logarithms is their power to simplify things. They take complicated operations like multiplication and turn them into simple addition. That single idea literally supercharged science and engineering for centuries. It really makes you wonder, doesn't it? What other complex problems out there are just waiting for the right tool, the right idea